Can you hear me now? Yeah, I think, sorry, I was muted, my fault. I muted myself before the session and I kept like this. I was saying I'm Valter, I'm from Toradex. I'm software engineer. In this session, I'm going to talk about containers. You have seen my face at the beginning of the presentation, but I think slides are definitely more interesting. So let's talk about containers. And this man is Malcolm McLean. Is the person who's credited about having popularized the use of shipping container in the world. He started in the 50s with the idea of loading trucks on ships. This didn't work too well because, of course, the trucks were taking space and they were not useful on board of a ship. Then he refined his idea and invented this concept of having a box where you can put a lot of things. And this box can be easily loaded on a truck and put on a ship. And that became quite popular. By the end of the 60s, he already had established commercial shipment routes between the US East Coast and Europe. And also, thanks to the war in Vietnam, he also managed to set up the same routes from the West Coast to Asia. And nowadays, shipping stuff in containers is definitely popular. It's probably the most popular way of shipping goods around the world. And many people recognize this idea as one of the things that changed even the global economy at that point. And the main reason behind the success of containers is costs. Loading and unloading things from ships was quite labor-intensive and time-consuming activity, and that was reflected on the cost. Before using containers, loading a ton of goods on a ship was costing around $6, and using containers, Mr. McLean managed to drop it to a few cents. So that definitely was giving some economical benefits. There are also some other side effects, like requiring less labor and also having these big harbors outside of the cities instead of inside them, change even the shape of many places in the world. What are the advantages of using containers and the keys for their success? A container is basically a standard package. There are two sizes defined, and every aspect of the box itself is super well standardized, from the way it opens to where you put all the different things. There are also some specific standards for specific kinds of containers, for example, refrigerated ones, and so on. Having such a high level of standardization allows you to have a shared infrastructure. You don't need to stop and think about, how can I fit this stuff inside the ship, or how can I lift those things and put them inside? Since all the containers are exactly the same from the outside, you can use standard cranes and perform kind of repetitive operations every time you need to load the ship or unload it or put these things on different vehicles. And that's another good point. You can use container on ships, but then when they reach their port of destination, you can unload them and put them on trucks or train, that's mostly common in Europe, to reach their final destination. So you don't need to unpack your goods. You can just take the box and put it on a different vehicle to drive its final miles to the destination. And that also improved efficiency of the transportation. As I said, container completely changed the global trade. Probably someone recognized the ship in this picture. It has become quite famous just a few weeks ago when it was stuck in the Suez Canal. But that's also another proof of how this idea and the whole industry that grew up around it really changed the world economics and the way we produce things in some places, consume them in different places, and how critical this is for the whole economy. Just having a ship blocking a canal can really introduce a lot of cascade effects over the economy. Okay, but how does this relate to software? We are here We are supposed to be talking about embedded hardware and software, so what's the relationship? The idea is that software containers, and I think in the software industry, for once, we just took the right word. Sometimes we do some stupid metaphors like vertical desktops or something like that. But yeah, software containers are really a way to package different kinds of application and services in the same format. So in a way that it's easy to understand from the outside and also easy to deploy. This means that also software containers are standardized and can be shipped and deployed very easily. And so this makes the whole software infrastructure a bit easier to maintain. The idea of the standard package is basically that in a container, we can package the application and all its user mode dependencies. A famous mantra in the software industry has always been, it works on my machine. Okay, with a container, you can kind of pack your machine, at least the user mode part, and ship it together with your application. So from the outside, we just have a container. Inside it, we can have very different things, but pretty much everything you need to run a specific application. How we can do this? It's relatively easy if you have never used containers before. This is a Docker file. With the Docker file, we can define the contents of a container. We start from something existing. Usually it's a distribution. You can also start from scratch, but it's not very common. For example, here we start from Debian. We start from a slim version. That means without some of the things you typically need to run it at boot on a real system. It's just a stripped down version. But for example, we have the package manager, so we can run some command. You can see the instruction in bold. And for example, here we run apt-get to install some specific packages. Of course, if you have a different distribution, you're going to use a different package manager. You can also run other commands like to change configuration files and so on. You can use copy to add some content taken from your machine into the container. And this is what you typically do to take your application and put it inside the container. And at the end, with cmd, you are telling the system what you're supposed to be running when the container starts. It's just one process, can be spawning other processes later. So you can, for example, run a script, but you have a single instruction. There are other things you can do in a Docker file, like setting up the environment and so on, but I don't want to complicate things. That's just a bare minimal Docker file, and I think it's enough to understand the idea. So you start from something, usually distribution, set it up to run your application, put your application inside, and tell the system this is what you need to start when you start my container. This allows us to build something that it's a container image that it's the equivalent of the metal box we have in the shipping industry. From the outside, the container image is pretty much a standard thing, a standard object. There is even a standard defining it, it's named OCI, if I remember correctly. And this allows us to also have a common infrastructure. So we have tools that allow us to build a container, starting from the Docker file and from probably some files on our machine. We have a container runtime that can take and run any container as long as it's for the right architecture. And we also can have a container registry, so a place where we can store all the different container images tagged with versions and so on, and easily download them on a device, on a PC, in the cloud, and run them. So the fact that our container are really all the same from the outside, again, allow us to build common infrastructure that we can reuse to run all the different kind of things we can fit inside a container. And as containers can be loaded on different kind of vehicles, ships, but also trains and trucks, we can also run containers. Probably this is where you have heard this term more often. You can run them on a local server, on your local PC when you're building something, but you can also run them on devices. You say running containers on devices, is that really a good idea? I mean, it's not a good idea to load a real container on a small boat like those guys are doing, But I think it's a good idea to run container on a device. Why I'm saying this? The point is that containers are designed to be efficient. I know that being a, let's say, old school embedded developer, I am an old school embedded developer. I started in 1999. When you hear about something coming from the cloud or from servers, you always think, okay, this stuff is probably big and inefficient and blah, blah, blah. Sometimes that's the truth, but sometimes it's not so true. And if we think about why containers are thriving in the cloud, for example, this is really related to efficiency. Containers are a very efficient way to run web services and so on, more efficient than full-blown virtual machines. And that's why many cloud providers prefer to run containers. And they can probably bill you a little less money, but they are probably going to be able to run many more containers compared to virtual machines, so they are going to get more money. So efficiency, it's really one of the, let's say, core features of the container model. And let's see how it works. I think there is a kind of misconception around containers. Sometimes you see containers referenced as virtual machines. This happens because they can solve the same kind of problems virtual machine can solve in some scenarios, but they are really different things. For example, I'm thinking about Open Embedded. The layer for virtual machines and container runtimes is named meta virtualization. But containers are really not the same thing as a virtual machine. Let's see it. Here we have the architecture, 20,000 feet view of the architecture of a Linux system. We have multiple processes running side by side. They are isolated from each other. They see the same file system, and through the file system, for example, device nodes, charter blocks devices, and so on, and through the API calls, they can talk with the kernel that it's at the end the piece of software that it's really talking with the actual hardware. In virtual machines, basically we take this and wrap it inside the virtual machine. Everything is still running in the same way it's running on the physical machine. Maybe even the kernel is not aware about being inside the virtual machine. But to perform this kind of magic, we need some additional components. Here it's named hypervisor. That it's taking the actual hardware and exposing some virtual instances of the same devices, like virtual network adapters and so on. So each system running inside the virtual machine has full control over the virtual machine, is isolated from other virtual machines running on the same system. You can even run different operating systems side by side this way. This is very useful for people willing to run servers or even stuff in the cloud. They can run multiple completely separated services, but on the other side, it requires quite some overhead. The hypervisor and the hardware virtualization are really demanding in terms of processing power and so on. On the other side, if you look at the same model about containers, we see that we still have just a single kernel. Our kernel is still running on top of the real hardware. This means that we cannot run different operating systems side by side, not even different versions of the kernel side by side. But on top of this, we still have, let's say, traditional processes with the file system, and that's the same things we have seen in the first slide. But we have this container that is a kind of sandbox where other processes can be running, and they have a different view of the file system. So we have multiple file system, we have 2 layers of isolation in this slide, but still the path from the process to the kernel is the same. So there is no overhead from the containerization in terms of time that our process needs to access the hardware at the end. Okay, we will have some additional overhead when we need to start the container, setting it up, and so on. But as soon as it's set up, it works. And containerization, it's not really leveraging specific hardware features as virtualization does, but it's mostly using features from the kernel. And many of those features have been there since quite a long time. Other C groups and so on have been added over time to implement this feature. But it's, let's say, just software. and it's not virtualizing any hardware. Okay, so a container, when it's running, we define it as a kind of package, but when we run it on our system, it's a kind of sandbox where our application or service can run in a well-defined environment. We define the environment using the Docker file, so we exactly know which version of which distribution, using which packages we are using. And so the environment is going to be reproduced exactly in the same way on all the different machines. Okay, that's the idea of it works on my machine. I take my machine and ship it. Okay, but again, we are not virtualizing any hardware here. We still have some disadvantages comparing to run application directly on top of the system. For sure, since we need a container runtime, can be Docker, Podman, Moby. This runtime has some footprint in terms of size, of storage, memory. And also, since we have multiple different base file systems running side by side, we probably need a bit more storage space and some more memory. Actually, as I said at the beginning, containers are about efficiency. So here the idea, compared to the approach of virtual machines, where you have virtual hard drives. So if you run 10 Linux virtual machines, you have 10 hard drives with 10 copies of the Linux distribution. With containers, things are organized in a more efficient way, and we have layers. So if we have different containers using the same base distribution, the base distribution is going to be stored only once as a layer. And this helps us saving some space. Of course, you probably need to design your containers in a way that it's reusing the same components. That can be a good idea. But if you do this, the amount of storage and memory you need is reduced. And I say also memory because also at runtime, the kernel is smart enough to understand that if you're loading a library that is coming from the same layer, even if you are in a different container, you don't need to allocate the memory twice. It's just shared like with any DLL. So this also helps in reducing the overhead. As I said, this model is really designed to be efficient. And so what does it mean to run my application as a container? First of all, as I already showed with the Docker file, we need to take our application and all its user mode dependencies and pack them together. So we need to create an environment where my application can run, and this environment can be reproduced on many servers, devices, or whatever. This idea allows us to limit some interdependencies. I mean, if we compare this to the, let's say, the traditional approach of building an embedded Linux image, when we build an embedded Linux image, we actually take different things, different runtimes. Maybe we take some let's say, modules coming from the user, the application, and whatever. And then we integrate everything together. We need to define which library we want to include, which version, and we need to find a match between the different requirements. This generates something that is very efficient. We have only one copy of every library we need. And so it's definitely probably the smallest image with this specific set of features. But on the other side, we also make a lot of things interdependent from each other. So, for example, if we have our engine managing the hardware of our embedded system, and then we have a web-based front end running on top of, I don't know, Node.js. We can find a way to integrate the Node.js runtime and our, let's say, engine on top of a specific version of Open Embedded. And okay, it takes some effort maybe, but everything is working quite well. But at some point, we have a security issue. There is a problem with Node.js, and I mean, it's easy to solve the issue. We just need to update Node.js. But if we update Node.js, we start a cascade of updates because maybe we need to update another library that's need another update in another library. And at the end, we are touching something that is used also by the engine. So this means that we have a very efficient, very small image, but that's probably, we are not going to update it too often, and we cannot update it too quickly because some updates can really touch some critical part of the system. With containers, we can have different versions of those libraries in different containers. So we can easily update, for example, the web server without touching the main application. So this makes your development cycle more more agile, and you should probably be able to fix this kind of, for example, security issues quite easily by updating a single component in your system. Also, many of those runtimes like Node.js, but Java, or .NET, or Python, whatever, already came in a way that can be easily reused in containers. So using containers make using this kind of, let's say, high-level runtimes on embedded devices much easier. The idea of using containers is really investing your time and resources into developing your solution. That can be an application or can be something more complex made up by multiple different things, but focusing on what is providing value to your customer rather than focusing on building and integrating the operating system. I mean, honestly, no one is going to buy your device because it's running the latest kernel or the most efficient operating system image. This may be needed to have a good device, but it's really not the reason why you are providing value to your customers. Value for an embedded device comes from the integration between hardware and software, and usually hardware and the application software. So, okay, but why we don't just use a distribution? I mean, honestly, in some scenarios, using a distribution is a perfectly good solution, a perfectly reasonable solution. The problem is that as long as you don't have actually a user in front of the system, or your user is not really interested into managing the system, that can be a bit tricky, because most of the popular distributions nowadays are designed to run in a server or desktop environment, where you can have a user taking care of, for example, applying updates or setting up the configuration interactively or something like this. So doing this on a device that needs to sit there and run for years, it's a bit different. Also, in terms of hardware standardization, if you're using embedded PCs, probably that's okay because those are PCs. But if you're using embedded devices like those we do with ARM SoCs or different kind of SoCs, then just booting your device, having some storage is completely different from device to device. So the layers you need to maintain to adapt the distribution to your hardware are becoming quite complex. So that's the reason why taking a standard off-the-shelf distribution and just run it on a device is not that easy. I know that probably out there we have some devices running Raspbian or something like this, but on the other side, I know also of many people that started by running this kind of off-the-shelf distribution and then had to figure out a way to at least heavily customize and close it to be able to run it on a real device. Oops, sorry, my presentation is stuck. Let me. Why is that moving forward? Okay, now it's working. Okay, running containers in embedded, I think, as I said, it's doable, but of course has also some specific challenges in terms of startup time, accessing the hardware, accessing the underlying OS. But before we start talking about the issues and problems, I wanted to show you how you can really build something using container on a device. Here's the Broccolinator. It's, as I said, an impractical sample application. It's impractical because, I mean, it's something I built in a couple of days, not in the weeks or months that are usually required to build a real embedded system. But on the other side, it's practical enough to show how you can use containers and some related technologies to solve a real-world problem. And the real-world problem, it's mostly a problem affecting people like me that have a super short-term memory for numbers. So when you go to the grocery shop, you take those fresh vegetables or fruits, and then you put them in a bag, and then you go to the scale, put them on the scale, and then you remove them on the scale, go back and check the number you have to input on the scale, and then go back and put them on the scale and finally put the number and get the price. The idea here is to have this kind of scale, supermarket scale, that it's able to recognize stuff that you put on the plate. So it's solving at least my issue, but I feel other people have the same problem. Anyway, I mean, this kind of solution can really make people's life better and justify a new product. And for some people, like for example, old people with limited sightseeing or having issues using keyboards or whatever, this can really improve their life. So what we need to build such a system, such a device, we need to be able to read the weight from a load cell. That's a scale. That's a minimal requirement. Then we need to recognize what we are putting on the scale. And to do this, we can use machine learning. So we can have a neural network that is trained to recognize the different kinds of vegetables, and it's able to do it. We probably also need to provide a local user interface, because the person standing in front of the scale wants to know what the machine has actually recognized, what's the weight, and what is going to be the final price. And probably the shop owner, mostly if it's a supermarket, may also want to know some information about, for example, how many times the scale has been used, which kind of vegetables have been weighted, how much stuff has been sold. This can be useful for making statistics, but also just for order new stock and whatever. So how we can make such a device? First of all, I want to show it running. The first frame, it's blurred, but the video should be fine. Please tell me in the chat if there is something wrong, but I will try to describe what's happening. So even if you don't see it, should be good enough to understand. So we have some vegetables that I just put on the scale. Here we have a small scale with the load cell. The load cell is connected to an analog to digital converter that through a SPI-like interface is talking with our board. It's an Apalis IMX8 from Tordex, of course. We have some additional hardware, a couple of LEDs, and the switch that we use to provide some basic feedback to the user and also to start the whole recognition and weighting process. Video is taken from this off-the-shelf network camera, and also you see the frames are shown in the local UI. It's made using Qt libraries, and here you can see how it works. Let's see on the software side. This is Portainer. It's just a UI to see what's running on a Docker system. I just used it to make this a bit more, let's say, easy to visualize. On our system, we have multiple containers running. Of course, one of them is Portainer itself. Then we have our Qt client. That is the graphical UI. We have some business logic. We are going to talk about this a bit later. We have chronograph, that it's a web front end. We are going to see it later in the presentation. We have our machine learning component. We have a Weston server. This is used to host the graphic UI. And we also have a container accessing the hardware, and InfluxDB, that's a database. And here you see with Portainer, you can see some information about the different containers, their output, so you can kind of monitor them. It's quite a useful tool when you're debugging. And now let's see the system working. So I'm going to take some vegetables and put them on the scale. Then I can just push my button, and the system is going to try to recognize them. It worked, so you can see also the weight, and it's cauliflower. But of course, we call it broccolinator, so we need to do the final test with broccoli. And here it is. And I mean, that's a video, so I know that it's working. That's a good thing about record the demo. It's recognizing our broccoli. And of course, if I don't put anything on the scale, you see the system is not able to recognize anything. Okay, yeah, that was also quite expected. Let's see what's happening on the back end. Here we have chronograph, that it's front end to query data stored into database. And with this, I can create some dashboard. So you can see here I have a dashboard reporting the average weight of broccoli and cauliflowers, and also if we had some like errors or which are the latest measurements and so on. So I can collect some data, show them in real time, generate some alarms or something like this. The interesting thing is that this is something that I didn't develop myself. It's just existing solution you can easily run on your system as a container. Okay, that's pretty much it. We can move forward. Let's go to stop the video. Okay, this is the architecture of the broccolinator. The each block you see in this diagram, it's a container running on the system. The one that are painted in green are things I developed. The one in blue are just, let's say, off-the-shelf software components that I just downloaded and executed on my system. I downloaded and executed them as containers, so I really didn't need to do anything specific to integrate them with my system. Just take them, just took them and run them. From the top, we have a hardware interface that is talking with the scale, with the switches and LEDs, so some kind of low-level interfaces. This is developed in C++. C and C++ are quite probably the best solution for this kind of things. We need some performances. We need to bit bang the SPI actually, because it's not the standard one. And if we have to deal with protocols, designing bits and bytes, I mean, this is where C and C++ really shine. So that's a good solution. We have a socket. It's just a UDP socket, exposing information from the scale and accepting some very simple commands to like turn on and off the LEDs. Everything is orchestrated, managed by a business logic. And for the business logic, I think it makes sense to use a more high-level language because we are talking about, let's say, more high-level operations. Probably we need to interface different kind of things, including maybe some kind of backend or something like this. And also, this software component may need to be customized for the different customers, different shopping chains, whatever. And this is where high-level languages probably are better suited. I use .NET. From Microsoft. If you don't like it, don't like Microsoft, you can use Node.js, you can use Python, you can use Java. So any kind of high-level language. We have to recognize our vegetables. And to do this, I said we use machine learning. So what I use is TensorFlow, actually TensorFlow Lite. That is a version that is designed to run on small devices. With TensorFlow, you can train your neural network. So basically, I took many pictures of the different kinds of vegetables and tag each one saying, okay, this is broccoli, this is cauliflower, this is broccoli again, broccoli, 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 broccoli. And then you feed all this information in the system, and it's generating a neural network. And then you can run the neural network. It's pretty easy to do in Python, since the heavy computational operations are performed by the runtime. Python is perfectly okay to build the glue logic around it. As I said, with Python, you can run the neural network on your system, and you can feed it with an image, and it's going to tell you, okay, this is 87% broccoli and 3% something else. So you can decide what's the threshold of recognition you want to enable, and you can get the information about what's sitting on your scale plate. We also, as I already mentioned, have a local UI that has been developed using the Qt library, libraries in C++, of course. You can also do this in Python nowadays. And that's a good solution if you want to have a nice looking UI. It wasn't nice looking in my demo, but just because I'm really bad at designing this kind of graphical UIs. And then we have the two off-the-shelf components. One is InfluxDB, since we need to take measurements at the end, weighting our vegetables, and we need to store them in a time series. InfluxDB is a very good solution. It's really designed to perform this kind of operations. And on top of this, Chronograph is coming from the same company. It's a nice web-based tool to create dashboards and graphics out of data you take from InfluxDB. So basically, without writing a single line of code, I can build my, let's say, browser-enabled front-end for my system. Okay. So this is another advantage of running containers. I can take existing software and pretty easily run it on my system. I don't have to integrate it in an OS image. I can just run on top of it. Now let's talk about the more challenging parts when running on a device. The first one, and the one for which probably I have bad news, is startup time. Of course, if you need to start your system and start the container runtime and create the, let's say, sandbox to run your container, this may take some time. So if you need to boot in 1-2 seconds, probably adding a container runtime on top of this may make this quite a hard to reach, to match requirement. On the other side, if 20-30 seconds are a reasonable time, this is the time it takes to boot our system to Horizon nowadays. So this is a more reasonable, let's say, target for your boot time. For some system, boot time is super critical, like in vehicle. I mean, I don't want to wait for 20 seconds before my dashboard. It's giving me some information in the car. But on another system, like industrial system, they're probably turned on once per day or once in their whole lifetime. So that's probably not so critical. But if you need to have a device that is booting super quickly, this is something you need to consider. You may also need to run multiple things, like I've been showing in the Broccolinator, so multiple services. For this, you have different choices. The one coming from Docker is named Docker Compose. With Docker Compose, you can define the different service. They use this more, let's say, server cloud terminology. You can define your services and also dependencies between them. So you can ensure that first, for example, in the Broccolinator, you start the hardware interface, then you start the business logic, and then all the other services that are relying on it. As I said before, the real value for an embedded device comes from the integration between hardware and software. And so our software at some point needs to talk with the hardware. I say that the container is a sort of sandbox. So by default, you are not able to access any hardware. You're not able to open something under /dev, whatever. And this makes a lot of sense if you're running on a server or in the cloud. I mean, in the cloud, it's even not your hardware, so you don't even own it. But if you are talking about an embedded device, probably you need to do this. But the good news is that it's pretty easy to dig holes into your sandbox, and leveraging the fact that on any Unix-based system, everything is a file. You can share, you can mount part of your local file system into the container. So you can mount /dev, but you can also mount specific devices. There is even an option in Docker to recreate the device node inside the container. So you are mounting a very specific device, or you can give access to a category, meaning major number of devices inside the container. So by design, the container is not accessing the hardware. It can access it, but you should allow it to do it. And I think that's not preventing you from doing anything you can do from a regular application on a Linux embedded system, but also providing some more security because you just limit the range of devices you can access. One reason to access the hardware usually is to have a graphical UI. This is something that is really not typical when running on servers and the cloud, but we need to do it on many embedded devices. You can run Wayland or X11. Probably Wayland is a more modern solution nowadays, but both are organized around the client-server model. For Wayland, it's client and compositor, but whatever. You just need to share a socket to have a basic functionality. In Wayland, you can also share memory, so you can have more efficient access to the graphic. You may also want to share the GPU inside the container, because if you want to use it to do acceleration and so on. In some cases, you can do this only on the server or compositor. In other cases, you need to do also from the application, because, for example, if you use OpenGL libraries in user mode, they are accessing the hardware anyway. You may also need to access the underlying operating system. The first requirement is to store some data. Containers are, let's say, transient by nature. So that means that you can create a container, run it, but at some point you may decide to stop it, update the image with the new version, and start it again. But everything that was stored inside the container file system at that point is lost. So to have some permanent data, you need to bind mount inside the container some folders from your local system. You can do this with actual folders, or you can use volumes that are basically folders that are created and managed by the container runtimes. At the end, it's the same thing. You are storing your data permanently, and this data is surviving restarts or updates of your container. You may also need to perform some other configuration operation. And again, this is something that is not happening on a server. You probably don't want to change the IP address of the server from inside a container running on it. Probably someone from IT is going to do this directly, but you may need to do this on an embedded device. If you are connecting your device to, like the Proclinator, to the network of the supermarket, you may need to configure using static IP or DHCP or whatever. Most of those configuration operations can be performed over dbus. So if you share the dbus socket into the container and you remap the user and group IDs of the users inside the container to those on the actual system, then you can use dbus in the same way as if you were running on top of your system. From a container, you may also want to check that the other containers are running, or maybe start a different container or update them, whatever. This is what Portainer does, the interface I've been showing before. You can easily do this by just sharing the Docker socket. Also, Docker is exposing a socket, and you can easily use it to perform this kind of operations. Of course, it makes sense that this, let's say, supervisor container is isolated from the network, so you don't have someone getting in and running something it's not supposed to be running. And then for other things like rebooting your system or blocking the updates when you're doing some critical operations, then you may use dbus, or you can find out your custom solution. Sometimes it's just a matter of sharing, again, a folder and locking a file, preventing the update system from applying the updates or rebooting your device. Okay, so after this explanation, I hope I convinced you that containers can be a good solution to run software on your system. I started working on embedded devices in 1999, and at that time the big discussion was around: is it worth to run a full-blown OS on my device, or should I keep writing a firmware? And at that time, some of the objections against running Linux or Windows CE or QNX or whatever on a device were exactly the same. It's going to take a lot more resources. It's going to add more abstraction layers in between. I'm not going to be able to write directly to the registers of my hardware or something like that. But nowadays we know that many devices are running a full-blown OS, Linux mostly. But on the other side, we know that there are still plenty of devices running a firmware, and it absolutely makes sense to write firmware in many scenarios. I think it's going to be the same with containers. We're going to see that containers can really fit well some scenarios, but in other scenarios, probably the, let's say, traditional approach of building your Linux image with Yocto Open Embedded, build root, PTX, this, whatever, it's more efficient. So it's really depending on your specific requirements. I mean, as containers didn't replace customized ships in the shipping industry, I mean, this is a very nice one. It's just basically a floating parking lot that it's used by Nissan to ship like 2,000 cars at time. I mean, it makes sense. You cannot fit a car inside a container. Even if you can do this, it's not efficient. You're wasting space or whatever. This ship is really designed for that specific purpose and makes sense. This ship is designed to ship livestock. So you don't want to fill a container with live pigs or cows or sheep. And so you can just load them on this kind of specifically built ship. Of course, this is happening in Australia, and that ship it's working there. And yeah, you can also have some super crazy requirements. Let me start this. This is super fun. If you need your ship to just turn vertical in the middle of the sea, okay, then probably here some custom design is absolutely justified. But I mean, apart from this joke, and that was just an excuse to show you this super cool piece of hardware. The point here is containers are not really a solution for each and every problem you can encounter when designing an embedded system, but they are another tool. And so in 2021, I think that knowing that you can solve some kind of problems and build system using containers, it's another skill that you can add to your tool set as an embedded developer. And sometime probably you can choose to use them, or you can decide to not use them because you know the advantages and disadvantages. When I started looking into this 3 years ago, our CEO, at the time it was leading innovation at Tordex, started talking about containers when we were just having coffee at the coffee machine. That's usually where big project starts. And I mean, I was looking at it and saying, no, I mean, what are you saying? I mean, we are doing embedded. This is stuff is for hipsters. It's stuff meant to run on the cloud and whatever. And a very good argument he had, I mean, we are running also Linux, and Linux is Unix, and Unix was really designed to run on mainframes, and it works perfectly also on embedded devices. So it's pretty natural that technologies find different application. You need to know the good and bad things about them to be able to choose which one is the best for your specific scenario. That's at least my idea. So if you want to play a bit more with containers, there are a few alternatives. Of course, now I'm doing some shameless self-promotion. We have Horizon. It's the project I'm working on at Tordex. It works on our devices. It's a small embedded Linux distribution that it's really designed to run containers on top of it. We provide Docker as container runtime. We provide also OT over-the-air updates, and we provide development tools that allow you to customize the OS itself without having to rebuild it from the sources. It's open source, so if you want, you can build it from the source. But if you just want to customize it, we provide some easy-to-use tool to do it. We also provide some development tools that allow you to use Visual Studio or Visual Studio Code to develop your application in C++, C and C++, C#, Python, and you're able to develop your application, deploy it on the device, debug it on the device, and then ship it as a container. So this is our offer, but there are plenty of other solutions. Balena is quite famous. Probably they were the first one proposing this container idea on embedded. Red Hat recently released Fedora IoT, that it's really designed to run applications as containers. They, of course, use Portainer, that is their own container runtime, but many of the concepts you have seen here perfectly apply. There is Hypriot, that it's a super small Linux image designed to run containers on a Raspberry Pi. You can also have other solutions that are integrating local containers and cloud-based backend, for example, Azure IoTS or Greengrass from AWS. Those are designed to take some components and instead of running them in the cloud where you can have some latencies, move them to the edge, to the local device, to be more, to reduce the latency, to be more responsive. Both allow you to run containers as applications. Actually, Azure IoT Edge only let you run application in containers. And if you want, if you have a Raspberry Pi on your desk, you can easily install Docker. You will find plenty of easy to follow instruction online. And from that point, you can start building your containers and running them. You can also build containers on your development machine. You don't need to build them on the target. It's usually building them on the development machine is more efficient. Lately, Docker has added some features like BuildX to really allow you to use to build containers for a different platform. So that can be quite efficient when you're developing, or if you have like a CI/CD server or something like this. Okay, that's pretty much it for my presentation. I think we still have 10 minutes left for the Q&A. So if you have questions, you can just write them in the chat or in the Slack channel, and I will try to reply.